So, here we go. We are on to Unit 7, Actual Chemistry. Last chapter was 2. But, as you can see, as I said on here, this is truly the foundation of everything else we're going to do in this class. All right? So from this point forward, if you don't understand this, just drop, okay?
Okay.
You got
Abby and I are like,
yeah. You earned half a credit. That's good enough. That's good enough. No, I'm kidding.
Reaching your water goals?
So I am noticing that the weekends are hard for me. I think it's because the water's not right beside me. But Saturday I also went on a 2-hour hike. And like my freshmen were like, well, why weren't you drinking during your hike? I'm like, well, I was trying to keep my 6- and 4-year-old alive so they weren't like falling off, you know. So I didn't drink during that 2-hour span. That killed me. And then yesterday still didn't make it. So.
Like a hip-mounted water bottle.
No,
Yeah.
I do agree with the weekend.
Chunk it at the end of the day.
Because like when you're not carrying something like this just with you the whole time, it's way more difficult.
And it's like right here
Yeah.
with me. So.
It's something to do almost.
Weekdays I'm hitting it every day. So room to grow. Room to grow. Room to grow. Okay. So we have hinted at this, but many chemical reactions are reversible. Medical? I'm just letting you know I can't talk today, guys, okay? I actually tried to sign a pass like this earlier with the wrong end of the pen, so I'm just saying it's Monday. In terms of chemistry, you may see on the AP test multiple different examples. So one could be a solid. One could be a solid dissolving and then recrystallizing. Solid dissolving and then crystallizing. Or electrons being lost and then gained in a redox reaction. We've already done that, right? We've done some redox stuff. And maybe hydrogen, H+ ions, being exchanged in an acid-base reaction. These are all kind of examples of things that can go both ways. But most of those reactions come with some kind of observable event. Where is Brendan? Wow, do we have 4 people left today? We have Brendan, 3. Allison,
I think it's
Vince, 3. Brendan's usually here to guess what the next thing's going to be.
Yeah,
So,
I know Brent.
so that's
Yeah.
what we noticed he was doing.
Yeah, because I feel like he would have been like observable right there. Shout out to Brendan. There you go, Brendan. There's a shout out. Examples could be color change, bubbles that would allow you to see the process is reversible. A dynamic equilibrium. So a dynamic equilibrium, it sounds real fancy when you put the word dynamic in front of it, exists when the rate of the forward reaction is equal to the rate of the backward reaction. And you're going to get to see this in a very simple lab on Thursday. At the beginning of a reversible reaction, the reactant, the brackets mean what? Concentration are high. Reactant concentrations are high, and as a result, the forward reaction is also high, right? Because if you start out with a lot of ingredients, right, you're going to make a lot of products. It's the opposite for the products. As the reaction proceeds, the reactant concentrations keep falling, and the forward rate of reaction decreases. Once again, true, but opposite for the products. So I kind of hinted to this graph in last chapter's notes, but you can see here, my amount of reactants is going down, my amount of products is going up until they become parallel, and that is where they are equal, at equilibrium. And you're going to get to see, you're going to make a graph just like this in lab on Thursday. Pretty cool, actually. It's going to kind of blow your mind, because it blows my mind every year, because it's just like, how does that work? But it's just science. So, anyways, Coulomb's law. Hydrogen bonding. No, it's neither. All right? After equilibrium. So, it sounds easy now, right? Just there's a forward reaction and a backward reaction, right?
Nothing much to it.
Not much to it. But after equilibrium is reached, a sudden introduction in reactants would result in a dramatic increase in the what reaction rate? Forward, yeah. In the forward reaction rate. Then you would establish a new equilibrium. So once we get to equilibrium, then we're going to change it, is what we're saying here. Flip it. I am recording, right? Thank goodness. Okay. When equilibrium is reached, it may appear on a macroscopic scale. What does macroscopic mean? Large, right? That the reaction has actually stopped. But if we looked on the microscopic scale, it would confirm actually it's still going. All right? But you just can't see it. At equilibrium, both products and reactants are present in the mixture. And if the products and reactants have observable differences like color, the reaction mixture should be a combination of the two. So I gave you an example of a reaction here. So my reactants here are red, and my products here are blue. If this is at equilibrium, what should it look like?
Purple.
Yes, it should look purple if it's at equilibrium. Because I'm going to have an equal mixture of the blue going forward and the red going backwards. So if I have colors, then this should look purple. Now, depending on the amounts of reactants and products, that will change the color. And you could actually estimate the relative numbers of reactants or products in the mixture. Like, for example, let's say there was like 10 moles total, right? And it was more red than blue, right? And you could figure out, okay, well then that means it's moving this way more than this way. So maybe I have 7 moles of products, only 3 moles of reactants. That's what I'm saying with that. And now, another K. Because if we don't have enough Ks already, it's not on the sheet, all right? But this is the most important K of chemistry. This is the equilibrium constant.
Okay.
So put stars here. It's another constant, is all there is to it. But the equilibrium constant is probably the most important constant in chemistry. And how many constants do we have so far? So many. We've got like N, remember that, 0.0821 liters times atmospheres over R, yeah. Liters times atmospheres divided by moles times Kelvin. You guys remember that? Sean? Never mind. All right. Not LATMMOLK. It's liters times atmospheres over moles times Kelvin.
He's confused.
Why does everyone remember this but Sean?
It's like the Truman Show. Remember that
Wasn't it
time?
Sean the one who's like, or was it Trey?
Yes, it was Trey.
It was Trey.
It was Trey.
It was Trey.
I thought
It was one of you guys over there.
I do.
It was Trey, because Trey's like, do we have to put the time symbol in there? Yeah. Anyways,
Well, I mean, on the yellow sheet.
on the yellow sheet, I mean, it's not there, is it?
No.
But
There's a space.
it ultimately doesn't matter. So, the equilibrium constant is sometimes you'll see as Kc, is given at a constant temperature. That is so important. Temperature cannot change for the equilibrium constant. So, we're going to write an equation here where A, B, C, and D are the stoichiometric coefficients. Of substances A, B, C, and D respectively. This is kind of a funny story. So in CP Chem, we just finished up going like moles to grams, moles to liters, moles to molecules. So then today, I taught them empirical formulas. So we're doing an empirical formula today. And they're like, does this still involve dimensional analysis? I'm like, yeah. Yeah. They're like, well, will there be more dimensional analysis after this? I'm like, yeah. Like we haven't even got to the mole ratio yet. So anyways, yeah, I thought that was really funny. So here's the equation. Kc is equal to the concentration of, let's write the equation first. My bad. Save that. Let's write the equation. Little a, big A. We're going to say this is AQ plus, am I on the screen? Yes. Little b, big B, AQ, is in equilibrium with little c, big C, AQ, plus little d, capital D, AQ. So that's my equation. So the little ones are my coefficients, yes?
Yep.
Little ones are the coefficients, and then the large letters would be my whatever, compound, element, so on and so forth. So if I was going to write a K expression for this equation, it would look like this. The concentration of big C to the power of little c times the concentration of capital D to the lowercase d over the concentration of big A to the little a times the concentration of big B to the power of the little b. So, what do we have here?
There's a lot of
Fraction.
A lot of letters. A lot of letters, but also what over what? Products over reactants. So not only is it products over reactants, it's also each individual thing raised to the power of its coefficient. That is the two biggest mistakes people make when they're doing this. Number one, they do reactants over products, which is wrong. All right, which is wrong. And they also forget to raise it to the coefficient. The two number one mistakes I see with my students, and I've seen it grading the international AP Chem test the last 2 years. Simple, silly, it's international. People take it all over the world, right? Simple, silly mistakes. Question set.
Stretch.
Just stretch? Okay. All right. So here we go. So concentration is going to represent equilibrium. So here we go. We have our concentration sign. This is going to represent our equilibrium concentrations, also known as the product. So this is what I just said. The product of the equilibrium concentrations of, this is weird, the product of the products, right? The products of the products raised to their stoichiometric powers divided by the product of the reactants raised to their stoichiometric powers.
It's after there's
Product, products, powers, product, reactants, powers. When you say product of the products, that's just kind of fun. Product of the products, product of the products.
sounds like
It's kind of fun to say, actually. KC is nice. Because remember the K last time, why it was tricky? Was it K? Yeah, it was K last chapter.
Negative or positive?
True. But what was hard about K last chapter? Guess what?
No units.
No units, right? There's no units. It's going to cancel out. Agreed? So there should be no units on K. So here are my side notes. All right, also known as I didn't know where else to put this. So I wrote side note. Side note number one, KC expressions do not, underline do not, emphasize that, include pure solids or liquids. Solids and liquids do not affect your equilibrium. So if you see something in an equation that has parentheses L or parentheses S after it, not included in the equilibrium expression. So now we have to start looking at states more.
It has to be aqueous or gaseous.
Got to be aqueous or gaseous, correct. You got it. So that's the first thing. Another mistake. Like, I'm basically covering all the mistakes people make on this in the first 10 minutes. Side note number 2. Using Kc, your equilibrium constant, at equilibrium gives you K, which that sounds stupid, okay? So using the Kc expression at equilibrium, you will get K. ...
Except.
At other points, so put parentheses, usually the beginning of the reaction. If we use the K expression at the beginning of the reaction before anything has started, you will get what is called Q. All right? And stay with me, Aubrey, I promise, okay? Q is the reaction quotient. The reaction quotient. So if it's at equilibrium, you get K. But if it's at any other part in the equation, and it's usually at the beginning, you get Q. Same equation. It's still products of reactants raised to their powers, all right? At equilibrium, you get K. But if you do it in the beginning of the reaction before it started, you get Q, the reaction quotient.
What are K and Q?
K is the equilibrium constant. Q is what that would be before the equation starts. The reaction quotient is really just something to compare the equilibrium constant to.
Okay.
Stay with me and you'll see what that'll make more sense in a second.
Gotcha.
Okay? Basically, Q is something we compare the equilibrium constant to. Stay with me. All right? It will make sense in a second. Just
Will it?
it will. I promise. Because I came up with something 2 years ago that was really good. All right? It was really good. Before that, nobody understood this. No, I'm kidding. Okay. All right?
I'm trusting the process.
So, trust the process. Example, decomposition of hydrogen peroxide. Write the expression for Kc. So, we have H2O2, which is going to be AQ, is in equilibrium with. So, we're really not writing a lot of straight arrows anymore at this point in our chemistry life. That, you guys remember what that breaks up into? O2, we're just going to say AQ for this purpose. It's really not, but that's fine. Plus H2O, also AQ. And then we have 2 and 2 here. So I would say write the Kc expression. So we're going to say K equals concentration of O2. We don't have to write that though, right? We assume it's in the 1. Times the concentration of H2O squared over the concentration of
Oh, wait a minute.
H2O2. Oh, wait a minute. What?
I thought I could cancel them out. I started doing it in my head.
Can't do that.
H2O2, yeah.
You can't do that because that's different things. There's nothing to cancel out here.
No,
All right?
I know.
Nothing to cancel out because it's different things squared.
I just haven't done math in so long. That's exciting.
Yeah. Oh, don't worry.
Oh, really?
We've got some math coming up.
Oh,
Please
boy.
don't say.
We got math
I
coming
wasn't
up.
as excited. Was like not in that purpose where I wish I had it. It was just like. this is
Well,
fun.
it's
Above
coming.
water right now. We're floating.
So, just be thinking ahead. Man, I've got a lot of like squareds and what if this was x and not this? It almost would be like 4x cubed over x squared.
I'm just not gonna think.
How would you solve that?
Keep
Flip it. We don't have to worry about that yet.
Yeah.
Consider the following. All right? We've got butanoic acid reacting with ethanol to make ester and ethyl butanoate in water. In 3 separate experiments, all the same temperature, that's key, equilibrium was achieved, and then the following data was collected. In each experiment, calculate the equilibrium constant and comment on the values. So we're going to write a Kc expression. So Kc is going to equal what?
The
Concentration of
the reaction.
C3 products. H7, CO2, C2,
Can you just say F?
H5. No. You want to write that out instead of the formula? I mean, if you want to, you can. It's not going to be super helpful. Times the concentration of H2O. Are we including H2O here?
Yes.
Why?
Yes.
It's a gas, right? If that would say H2O liquid, not part of it.
Would you just not put it in?
You would not even include it.
Okay, but you would still be able to do it, just without it.
You just close it.
You would do it without it.
Okay.
Done. Thank you. Just sit in there. Have a great day. You too. You too. No, you too.
You too.
You too.
I thought that was Eric from behind, and
Say
then
what?
I saw Eric, and my mind exploded.
I know. I was also confused when I saw Eric go to the door. And I saw
And then
similar
Eric
hair.
goes
I'm like,
out the door.
has time traveling actually happened? What if Eric from the future? What if that was Eric from the future? What would we have done? Like future Eric 6 months from today.
Look, he just closed the door and someone knocked. Like, it was
Yeah, but that's how
perfect
time travel works. Isn't it? When you
That's
least
what I'm
expect
saying,
it,
would have been
your future self
perfect
happens.
time.
What's the first question you're asking your future self, Eric, as he walks in the door?
What's poppin'?
Yeah. What's up?
Really?
No.
Ask how you did on the AP Chem test.
Yeah.
Oh.
I would have.
How many months from the future is this, Eric? We said 6 months.
You said 6.
You'll probably have your scores by then, yeah. You should. It'll be close.
I'm not quite.
You probably wouldn't have them yet. It's
Oh,
usually
really?
end of July, early August.
I feel like I'm really concerned because why would I come back in time?
Like, Eric, what's one thing that you don't know yet that you want to find out?
Falling apart? Is that what I'm
Do you know where you're going to college?
You
Yeah.
came back to get
Okay.
me.
Yeah, between now and then,
What can happen?
lots.
Yeah. I'll find out. See, a lot can happen. You probably don't know what would be.
I would ask my future self about stocks, is what I would.
Oh, see, that's smart.
Pull a little Back to the Future. Have you guys seen Back to the Future?
Back to the Future hasn't actually.
Jacob, have you seen Back to the Future? Because I think we've discussed that you haven't.
I might have like kind of glimpsed in it while it was on the TV.
Oh my goodness.
Those kicks are
After the AP test, I know what we're doing.
Those kicks are really nice.
Back to the Future
All 3 of them
marathon.
are good.
Yeah.
Oh,
Yes.
great.
I've only watched it
Are we watching Pirates also?
Yeah, we have.
Potentially.
I can throw down in ping pong if we're doing that again.
Ping pong?
That's my promise.
Oh, we always play ping pong after the AP Chem test. So
Okay, we'll be good.
we'll get one.
That's pretty good.
Yeah. I have access. Over the concentration of C3H7CO2H times the concentration of C2H5OH. So, what is it asking us to do? It's asking us to calculate the equilibrium constant and comment on the values. So, K is going to equal, let's do experiment number 1,
4.
right? It's going to be 20 moles, right? Times what?
20 moles.
20 moles, right? I'm just subbing in my numbers. Over 10 moles times 10 moles. 20 times 20 is 400. 10 times 10 is
100.
100. 400 divided by 100 is
4.
K equals 4.
There's just
No
no units.
units.
Just
No units.
You know,
What about the second trial quick in our heads? I'm going to have 10 times 40, which is
This is also
400, divided by
100.
100. So that's going to be 4. 12 times 10 is 120, divided by 30 times 1. 4. Why are they all the same?
equilibrium.
They're all, nope, not equilibrium.
No.
They're all the same because,
Same temperature.
yes, nice. Temperature is constant. They are all the same because temperature is constant. And it's time to drink water.
Do you think I have time to go to the bathroom? I'll just take a picture of what I missed.
I mean, we can take a quick 2-minute break.
Oh.
I have a question.
taken out by a bus, but we don't really
Wow.
know based on a prophecy.
A lot just happened. A lot just
Did I
happened.
miss any chemistry though?
You did not. We waited for you.
That's all that matters.
Did you? Was there people in the hallway still? Was it safe?
There were like 2 people with lunch boxes, but it was Mr. Ruff and a kid. So I counted Mr. Ruff.
But they kind of look the same. So
Yeah,
it's true.
Fired.
Yeah.
It's true. I'm right. That's why it's funny, right? All right. So here we go.
Is it still recording that whole time?
I paused.
Oh.
And I know. Sorry, you guys missed the psychic. Ask Jacob about his bus. So we're now going to move on to calculations where initial amounts are known and then equilibrium is established. So this is going to be using what we call ice tables. All right? Or I like to say ice ice baby, because why not? So, dun, 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 dun. Who stole it from who?
Queen. Vanilla Ice stole it from Queen.
Did they win that lawsuit? Didn't Queen?
What was the Queen song? It was
Pressure
Under pressure.
Oh yeah, yeah, yeah.
pushing down on me. All right, here we go.
Get back.
So, using the reaction, so we're still using the same reaction, I believe. Yes. Using the reaction in the case he calculated in question 1, calculate the number of moles of each substance present at equilibrium when 1 mole of butanoic acid and 2 moles of ethanol are mixed at the same temperature. So, before we do this, in any equilibrium, the reaction is incomplete. The reaction is incomplete, meaning we can't predict the number of moles of products purely based on stoic, like we can in reactions that go to completion. In order to account for this, we use an ice table. ICE all caps. So we're going to be using ice tables. So first thing I like to do is write out my reaction as it is. So do it just like I'm doing it. So we have C3H7CO2H gas plus C2H5OH gas is in equilibrium with C3H, can't read my own handwriting, H7?
Yep.
H7CO2H, right?
C2H5.
CO2C2H5
Yes.
gas plus H2O gas. So the first thing I'm going to write is my initial. What I'm starting out with my initial amount. I. Yes. So what is my initial amount of C3H7CO2H?
One. Yes.
1 mole, right? If you want to write out moles, you can. I don't care. What is my initial amount of
2.
ethanol? 2. What is my initial amount of products? We know.
Oh, we do.
4 times that, right? It's got to sum up to 8. 3. No, 2. We can't. Is this the thing that we can't know?
Go on, you're almost there.
0.
0.
Oh, that's right.
There's no products yet, right?
Facts.
At the initial conditions, I have no products. Agreed? Yes?
So this is why classrooms start.
Yes.
Don't
All right? It's 0. It's 0. Now, we have to figure out what is my change.
Oh, C.
What is my change?
Oh, is this going to be spelling eyes?
What is my change?
That's crazy.
So, how much is this going to change?
0.
4.
Why are you throwing out random numbers?
K.
Do we know? No.
We can't. We don't.
So, am I going to be making more or less? Am I going to be having less products at equilibrium or more?
More product. Less reaction.
Less reactants, more products, right?
Yeah.
So minus X, right?
Oh no.
Minus X. And over here, however much this goes down should be how much these go up. Agreed?
Valid.
Yes?
So that's okay.
So I'm just saying, so it up here, right? We said in any equilibrium the reaction is incomplete, meaning we can't predict the number of moles purely based on stoic. So we're saying that this is going to change. I'm going to have less reactants at equilibrium, right?
Yeah.
If I'm making products, I have to have less products than what I'm saying it backwards. I have to have less reactants than what I started with,
Okay.
right?
Yes.
But I don't know how much I'm using.
Yes.
I just know it's changing. I know that my reactants are going down and my products are going up.
Okay.
And I'm just saying X. Could be any letter, right? But you know, math. We usually use X. Guess what E stands for? Equilibrium.
Important.
E is equilibrium. And in fact, some people actually call this a Rice table because your R is your reaction.
I like that.
So, whatever you want to do.
Nice rice.
I always write the reactions. Maybe you want to call it a Rice table. I don't care. But at equilibrium, what am I going to have for my equilibrium concentration of this?
1 minus X.
1 minus X.
Great.
What am I going to have for my equilibrium concentration of this?
2 minus X.
2 minus X. Equilibrium concentration of this?
X.
X. Equilibrium concentration of water?
X.
X.
We're done.
Okay? We're not done.
Darn it.
All right? So using the reaction in the case he calculated in question 1, calculate the number of moles of each substance present at equilibrium. So I now have to set this into a K equation, right?
Oh.
So I'm going to say that, what is my K? 4. I'm going to say that 4 is equal to, what are my products? X times X, which is going to be, is it okay if I go to X squared? You guys okay with that? X squared over
This looks very math.
1 minus X times 2 minus X. Yes? So you have a little bit of factoring. So 4 equals X squared over X squared minus, come on, do your FOIL. No.
2 minus 3X plus X.
X squared minus
3X.
3X
Plus 2.
plus 2. Agreed?
Sure.
Yes.
During.
Factoring, a little bit of factoring here. A little bit of factoring.
Okay. True.
So, to simplify this more, when we multiply, it's going to be 4x squared minus 12x plus 8 equals x squared, right? Or, to simplify this a little bit more, 3x squared minus 12x plus 8 equals 0. How are we going to solve that?
Quadratic formula.
Yep,
Factor it.
quadratic
Not
formula.
worth trying.
Get out your calculator and do it. Just type it in your calculator.
My life is just slowly going.
All right. Quadratic formula. Like, when you put it in your calculator, you're going to get how many answers?
2.
2. One is going to be positive, and one's going to be negative. Can we have a negative molar concentration?
No.
No, no, no. So you've got to use the positive one your calculator spits out. Do you see why your graphing calculator is important now?
Yeah, I also can't get my calculator.
Still have stat plots on.
Yeah, we're done with stat plots. Okay.
Oh, well, that's at least.
Can also distract me to find the.
What is A? You guys got to know what A, B, and C is, okay? You're an AP Chem. I have it up there. There you go. There's the, it's up on the yellow sheet.
I'm just reading.
X squared minus 12. checking my work.
mistakes on. Just so that-
Checking your work.
They're both positive.
How many decimals?
They are both positive.
2 or 3? I did 3. What did your calculator spit out? How many? A bunch?
Yeah, a bunch.
Let's do 3. This isn't like a very sig diggy thing I would grade sig digs on. So, really the only number we have to base sig digs off is 4. So, let's do 3 to the decimal for funsies. What did you get for x?
Two things.
But what's the positive?
They're both
Both
positive.
positive.
Oh,
Yeah.
what did you get?
3.155 or 0.845.
Well, one doesn't make sense. It's not going to be 3, right?
Because you can't have a negative.
What?
Because that would mean at equilibrium you have negative moles.
Yeah, you can't have 3 because it's going to give you negative moles. It has to be the 0.845, right?
Yeah.
It's got to be the 0.845. Now the good news is you're not going to have to do quadratic formula on the AP Chem test. All right?
But on your test report?
I don't know. I'm not sure. It just depends year to year when I decide. But you've got it. What? What?
So that way you just will be able to factor it?
I'm going to stay with me. Stay tuned. All right? Stay tuned. Okay? Stay tuned and you'll see why later. So, but we haven't answered our question yet. Because it said, what? Calculate the number of moles of each substance present at equilibrium. I just solved for x. So what's my concentration of C3H7CO2 at equilibrium? It's going to be 1 minus 0.845. So what's that going to be? 0.155 moles, right? And what's it going to be for this one? 2 minus x, 1.155. And these are both going to be 0.845 moles and 0.845 moles. So after you solve for x, then you still have more work to do. So we're just solving for each one. What you'll usually see is they'll tell you what one of these is at equilibrium. So they'll say at equilibrium this is 2. Then you solve for x there and then substitute that in for the other ones. I'll show you one like that in a second. So your first ice table, kind of fun. All right. I start with the hard stuff, make it easier after here. So there's some quadratic formula in chemistry. Kind of fun.
I'm not thrilled for the number of homework questions we're going to end up with.
Another ester. I'm still working through that.
Okay.
Another ester, ethyl ethanoate, can be formed by the reaction of ethene with ethanoic acid
Why would it be so long?
in an inert solvent, because it just is. All right. According to the equation, C2H4 plus C3H2O, which is in equilibrium with CH2CO2, C2H5. In one experiment, 0.5 moles of ethene were allowed to react with 0.250 moles of ethanoic acid, and the total volume of the mixture, oh snap. Now I have volume? Shoot, now I have moles and volume. So what do I have to do with that?
Cancel?
Figure out concentration.
Oh, no.
Oh, you can do that.
Oh yeah.
Oh, no.
When equilibrium has been established, the mixture was found to contain 0.220 moles of ester. So here we now know what one of them is at equilibrium.
Double.
Makes it a lot easier, right? So, calculate the molar concentration of all 3 substances present at equilibrium and hence the value of Kc. I was in a very hensey mood when I wrote this. So, what's our first step going to be? Write the equation.
Yeah.
Write the equation. We're going to ice it.
Yes, Mom.
We're going to ice it.
Right.
Good job, Mom.
Got it.
We're going to rice it.
Nice.
So, C, rice, baby, C2H4.
I'm assuming this is all gas.
Yep,
Okay.
these are all gases. If it doesn't say, we know that it's going to all be gases or aqueous. Plus CH3 COOH is in equilibrium with CH3 CO2 C2H5. So here's my R. My initial What's my initial concentration of my products?
0.24 Fe.
0.
Yes.
I'm not starting with anything for my products, right? Agreed?
Always? Well,
Not necessarily. For now. For now. For now. For now. It always gets more complicated.
You said
Until I say we are done covering content, it's going to keep getting harder from this point forward. Until we start watching Back to the Future and Pirates of the Caribbean, it's going to keep getting harder. So, initial for C2H4 is going to be what?
1 molar.
0.5 moles divided by 500 milliliters, right? But 500 milliliters is how many liters? 5. So 0.5 divided by 0.5 is 1 molar. 0.5 divided by 0.5? 0.5 moles divided by 0.5 liters. 1 molar. Lots of little steps here, right? So many ways to make a mistake.
oh, that's
So many ways to make a mistake.
it's so
And now you can start to see why we grade the AP test why we do, right? Because if you make a mistake here but do the rest good, you're still going to get like 4 out of 5 on this question. Initial concentration of this, 0.250 divided by 0.5 is going to be
5 molar.
0.25 divided by 0.5 is
0.5.
0.5. 0.5 molar. 0.5 molar. Change.
Minus X.
Minus X. Imagine just writing these down and not being able to see this like written out live. Like that would make not a lot of sense.
Yeah. If the coefficient in front of the ethanoic acid were 2, it would be
Ah.
minus 2x.
Yes,
Okay.
we'll do one like that.
Okay.
We're starting basic here, but let's say there was a coefficient of 2 here, then this would have been minus 2x. But we're starting out with all coefficients of 1. I'm baby stepping you into it, okay? So if there's a coefficient, then it's minus 2x or plus 2x. Good call. Equilibrium is 1 minus x. I have 0.5 minus x and x. But they told us something, right? I believe they did.
0.22.
When equilibrium has been established, the mixture was found to contain 0.220 moles of ester.
That's X.
So I'm going to take my 0.220 moles divided by
0.5.
0.5 liters, and what do I get?
0.440.
0.44 molar, which is X.
That's how you do that.
So I have 0.44 molar here. What is it going to be for this one? 0.5 minus 0.44 is 0.06. 1 minus 0.44 is 0.56. So, calculate the molar concentration. Check. But now I have to calculate K. Do it. Calculate your K. Now we're down to like 2 questions on the test. No, I'm kidding.
Nobody likes
I think it's pleasant.
This isn't bad. It's just, it's okay. I see that there. It's okay. All right. It just takes steps, takes time, takes some patience. On the screen, yes. Kc equals concentrations. What'd you get, Seth?
13.
I had 13.1.
Me too.
13.1. That is a very, very, very large K. Which means, let's see if you guys can figure this out, and we'll stop for this point. What is favored?
What?
Reactants or products?
Products.
Products are highly favored, right?
Because it's above.
So this is going all the way, almost pretty much all the way to what? Completion, right? Because it's such a high K value, you have a huge amount of products, right? Over a small amount of reactants. So that's where we're going to go with this tomorrow. Which way is favored? Which way is it going to shift? That's a perfect place to stop for tonight. Nice work, Marin.
Do we need our book?